Welcome to the session on XML databases of the Lecture NoSQL databases. The lecture is based on my textbook Advanced Data Management, where you can find more information. We will cover XML databases, XML query languages, and XML data management today. XML is the extensible markup language standardized by the W3C. XML is structured by tags. A tag is a label for a section of data. An element is such a section of data. It begins with an opening tag name and ends with a matching ending tag name. Inside an element there may be arbitrary text or other nested elements, or it might be an empty element. A major condition for XML documents is well-formedness. A first requirement for well-formedness is proper nesting. Proper nesting means that start and end tags have to be appropriately ordered. More formally, every start tag must have a unique matching end tag that is in the context of the same parent element. A further requirement for well-formedness is that every document must have a single top-level element called the root node. In addition, elements can have attributes that are specified by name-value pairs inside the starting tag of the element. While an element may have several attributes, a further requirement for well-formedness is that each attribute name can only occur once inside one element. So-called XML parsers check for well-formedness. XML documents can be represented by trees where the elements and the attributes are the nodes in the tree. The child nodes of an element are its attributes and sub-elements. The text inside an element is also a child node, called a text node. The tree structure comes from the fact that each node has a single parent node. We will look at an example of a reservation system for hotel rooms. Reservation system is the root node. It has a child node called hotel, which also has an attribute. The hotel node has further sub-elements as child nodes. Here we see the tree representation of the example XML document. Note that the attribute hotel ID has its own node. Moreover, each text inside an element has its own text node. In addition to well-formedness, we can also require validity of XML documents. We need a schema definition against which we can check validity. For XML documents, a schema definition can be given as a document type definition. Or the schema can be given by an XML schema document, which is itself an XML document. Now let's look at some standardized query languages for XML. Querying an XML document corresponds to finding nodes in the XML tree. As we will see on the next slide, there is a certain terminology for navigation in the tree. For filtering the results, we can also specify properties of the nodes. Three standards are XPath, XQuery, and XSLT. With the XPath, we can simply navigate in the tree, whereas with XQuery, we can add and modify elements in the answer document. With XSLT, we can, for example, transform XML into other output formats. Now we have a closer look at the terminology. When navigating the tree, there's always a current context node called self. The nodes on the path from the self node to the root node are called ancestors. The parent node is the direct ancestor. All nodes on path from the self node to the leaf nodes are called descendants of the self node. Direct descendants are the child nodes. Nodes that have the same parent as the self node are called its siblings. There may be other nodes preceding the self node in the XML document or other nodes following the self node in the XML document. We will now look more closely at XPath. With XPath, you can basically navigate in the XML tree to locate parts of it. Each navigation path consists of a sequence of individual steps. Each step consists of a navigation axis, followed by a double colon, then a node test, and one or more predicates in brackets. With a step, we identify a set of nodes, which depends on the current node in the tree, the context node self, as well as the structure of the XML tree and the type of the node. Predicates can be evaluated to true or false. They act as a filter, and we only take those nodes for which the predicate is true. The node test checks for attribute or element names, or the content and type of nodes. If the node test follows an element axis, it can check for the matching element name. The asterisk is used as a wildcard and matches all sub-elements. The node test text matches any text node, whereas the node test node matches any node. When the node test follows an attribute axis, we choose from all element nodes the one attribute with the appropriate attribute name in the node test. Again, the asterisk is used as a wildcard to select all attributes of the context node. We see here an example consisting of several steps. Starting from the root node, we look for an element called hotel. With the predicate, we choose only those hotels that have a location element as a child node that itself has the text Newtown in it. If we have found such a hotel, we read out the hotel ID attribute of the hotel element. To make XPath better readable, usually abbreviated notation is used. Next, we come to some XQuery details. XQuery is a declarative language consisting of FLOWR expressions. XQuery results can be sets of items consisting of either atomic values, simple types, or XML elements, attributes, or text nodes. The resulting document can be different from the input document because we can add elements and attributes to it. XQuery uses XPath as a sublanguage. XQueries are also called FLOWR expressions due to the clauses for, let, order, where, and return. The for clause is used for iteration over a stream of tuples. The let clause assigns an expression to a variable, but without iteration. With the order clause, we can sort the tuples, whereas with the where clause, we can filter the tuples. Lastly, the return clause defines the query result. In the example, we see that we can add a new root node called hotels to the output. With the let clause, we load the input document. With the for clause, we iterate over the hotel names. We return each hotel name inside a new element. Next, we look at some internals of XML management. Numbering schemes are important to assign a unique identifier to each node in an XML tree. When updates are allowed in the XML document, we usually prefer a numbering scheme for which the number of nodes to be renumbered is minimized. The simplest numbering scheme is pre-order traversal of the tree. In the pre-order traversal, we have an increasing counter for each node. First, we number the root node and then go on recursively for all child nodes. In an update, in the worst case, all nodes have to be renumbered. We see here an example of pre-order traversal of the tree. We start with a root node and give it a 0. The highest numbered node is the rightmost child node, leaf node, in the tree. The post-order numbering is an alternative to the pre-order numbering. The root node is numbered last. The numbering starts with the leftmost leaf node as the first node, numbered 0 in our case. Again, when the XML document is updated, in the worst case, all nodes have to be renumbered. We can combine pre- and post-order numbering. When navigating the tree, we can compare the context node self with another node W. We compare both the pre-order and the post-order numbering of the self node and W. With the help of both pre- and post-order numbering, we can more easily decide whether W is an ancestor, a descendant, a preceding, or a following node of the self node. There are the following navigation rules with pre- and post numbering. W is an ancestor if the pre-order numbering is less than the one of the self node and the post-order numbering is greater than the one of the self node. W is a descendant if the pre-order numbering is greater than the one of the self node and the post-order numbering is less than the one of the self node. W is preceding if the pre-order numbering is less than the pre-order numbering of the self node and also the post-order numbering is less than the post-order numbering of the self node. W is following is if both pre- and post-order numbering are greater than the ones of the self node. The combination of pre- and post-order numbering can be shown by a diagram where the x-axis is the pre-order numbering and the y-axis is the post-order numbering. We now position all nodes of the tree in this plane according to their pre- and post-order numbering. When the self node is the center, we can now locate all ancestors, descendants, preceding and following nodes. Here is an example of combined pre- and post-order numbering. When D is the context node, its ancestors are located in the left upper quadrant. Its descendants are located in the right lower quadrant. Preceding nodes are located in the left lower quadrant. Following nodes are located in the right upper quadrant. As an alternative to pre- or post-order traversal, we can also use prefix numbering. Numbering occurs according to the levels in the XML tree. Prefix numbering is modification friendly. When inserting a new node, only the siblings of this node and their subtrees have to be renumbered. A common prefix numbering scheme is called Dewey ID. Each level in the tree has its own counter. As the final ID, we concatenate all counters of the path of all ancestors to the root node and separate them by a dot. It is now easy to see on which level the node is located and which node is the parent node in the tree. Here we see an example of Dewey ID numbering. The root node is on the first level and just has one counter, whereas the leaf nodes are on the third level and have 3 counters concatenated by dots. Lastly, we look at some XML database systems. ExistDB is an open source database system which has been around for more than 10 years and supports many of the XML-related standards. It supports XPath, XQuery, and XSLT, as well as automated indexing. Schemas and schema validation are optional, so that Exist can save XML documents without a schema. It also supports updates as well as different APIs. Another open source system is BaseX, which is written in Java and supports ACID transactions. It offers several indexing functionalities and supports very large XML instances. It accepts XPath and XQuery expressions and has API support for XQuery and XML::db. This was the session on XML databases. Thank you for listening.